Welcome back. We just ended and we talked about our E2 and some subtle nuances with our E2 reaction. And I kind of feel a table coming on. So I just want to give us a little baby flow chart here. So if we take a look at our electrophiles and we look at our different options for electrophiles, one of the first things we are starting to look at is whether or not it's primary, secondary, or tertiary. Now, once we figure that out, it's going to help us try and figure out, do we have an SN2 or an E2? And then our next series of videos is SN1, E1. We're not done. We're going to have 4 different options of things that can happen to our electrophiles. And so let's kind of stop and list before we get a little bit too far. So what did we do when we had a primary? We noticed that we had SN2. All right, now I want to add to that because our list that we had of nucleophiles and bases gave us both of these, gave us an SN2. But now that we've learned that our bases have a size, I'm going to add an exception, and that is that LDA. Our LDA is too big to be a nucleophile. It is not going to do an SN2. Our size matters. So in fact, all of these are going to give you an SN2 except your LDA. So if I were to take this reaction with our LDA, you're still going to get the elimination. You're not going to get ever that. Okay, you will get this one and not this one. Perfect. Okay, now all right, our secondaries, boy, they're the confusing ones, right? So when we look at that, we broke it into, if we had a nucleophile, we had an SN2. If we had a base, we have an E2. And now we're going to break it up farther for size matters. Small, large. Okay, so your secondaries are really the tricky ones. You've got some choices there. And then what about our tertiary? Our tertiary didn't do SN2, only E2. And in this case, our size isn't going to necessarily matter because that would be nice and symmetrical. But what if your tertiary wasn't symmetrical? Then you still want to take a look at your base and look at your size matters. Small, large. Okay. I love it. All right, so we have one more caveat with our E2. Just like our SN2, it's a collision. It is a collision, and we saw that that collision affected any stereochemistry we might have. Oh, any stereocenters. I tried to combine 2 concepts there. So what does your gut tell you in E2 also? All right, here is my favorite part of an E2. If you've got a model set, this would be a fun time to grab it. We have one last caveat for an E2. It turns out that nice flow in our mechanism that I showed you. Let's draw it again. Let's take any kind of our base. Our mechanism all happens in one big flow. It's like a waterfall. Those electrons are all going into specific anti-bonding orbitals. Okay, I love it. So if we're going into those anti-bonding orbitals, just like an SN2, that means there's going to be some specific orientations in space. So for an SN2, that gave us inversion. Remember, we inverted the stereocenter. For an E2, what it means is that your beta hydrogen and your leaving group must be anti-periplanar. What? Where have we heard that before? Our Newman projections. Anti-periplanar is exact opposite, 180 degrees from each other. Okay. So that means the reaction that we are looking at right here, what would that need to look like? That would need to look like, let's put our beta hydrogen right up here. That means that your leaving group has to be down here. So it turns out for this one, these are hydrogens, and then this doesn't matter. There's your other carbon. So this needs to be anti-periplanar. We have to have your beta hydrogen and your leaving group 180 degrees apart. So that's awesome. We get to bring back Newman projections. Aren't you excited? Haven't you missed those from Unit 1? Okay, but here's the fun part. So one of the reasons we draw this circle here, the bond that we usually rotate, look at, that's the bond that is in your Newman projection. You are putting your eyeball right here. And you could look at it from the other way as well. I'm just always going to try and draw them the same way. It makes it a little bit easier. So that's your Newman projection. But remember, where do we make our double bond? Don't you make your double bond between your leaving group and your beta hydrogen? So you're about to make the double bond right where your Newman projection is. So what I like to do is let my Newman projection show me which double bond you're gonna make. Now here's where it's awesome. As soon as you make a double bond, we learned in our last video, you cannot bond rotate. So your Newman projection, I'm gonna add to it. You're about to make this double bond, okay? This is this. This is the same thing. And then I'm going to keep, you lose that leaving group. Well, on this side of my molecule then, I have the other part of my molecule and a hydrogen. And then on this side, I've got these two hydrogens. Now, in this case, it doesn't matter. There is no cis and trans. But you know where we're headed for this. We are headed to where it does matter. So let's take one of these and let's apply it in a way that it matters. So I'm going to go ahead and give us a specific orientation in space. And let's use our small base. And let's figure out what just happened there. Okay, what in the world? Let me draw this a little bit better. What in the world just happened there? Okay. And why is that going to matter? Okay, so let's go through our process. Number one, here's our leaving group, and we are on a secondary electrophile right there. This is a base, not a nucleophile, and this is our matching solvent. So this is a recipe for E2, okay? And now we've learned that we check our size. Size matters. This is small. So small lets us choose the right beta hydrogen. We have two options for beta hydrogen. Which one do we choose with our small base? This one. Okay, now this is a situation where we need to use a Newman projection because our leaving group and our beta hydrogen need to be anti-periplanar. So we would take a model set and we would model this, and we would put our eyeball, if we want to follow our last drawing, let's put our eyeball right here on that carbon, and we need the Newman projection where we're going to make the double bond. If it helps you to draw the mechanism, let me draw it flat real quick first, and let's draw our mechanism. Our base is coming in. We are taking, let's color code, okay? This hydrogen, these electrons are making your double bond, and you're losing your leaving group. So the bond that we want in our Newman projection is this one. So put your eyeball over here, and let's draw that Newman projection. Remember, our best Newman projections are staggered. I'm going to go ahead and turn this in my mind, and I'm going to put that beta hydrogen up here. So let's take a little model set and let's double check we know what we're doing on that. So you don't have to build the whole thing, but make sure your model set actually matches what is on the drawing. Okay, these are now bolds and dashes, so they have to match. So I'm going to take that and I'm going to make that match, and I'm literally building a model set while I'm making this video with you. So I am putting that hydrogen in the back, and then I'm making sure that on this other side of our compound, I'm going to switch it and make sure that my bromine is right out front. And now we're going to do these in class with my webcam and actually do some modeling on these on Tuesday. So I need you to watch these videos before Tuesday. Okay, so now I'm literally going to turn this, and I'm going to draw that model set, and I'm going to put the hydrogen up top. And then that is going to give me this. And then in the back, I'm putting the bromine down. So that means that I've got a hydrogen over here and a methyl over there. So really, this is the hard part. This one takes work. This one takes work. Right here, videos don't do it justice. You actually want to model this. And again, like I said, we're going to do this in class. And why does this need a model set? Because these are very specific. These are stereocenters. So once we've identified our beta hydrogen and our bromine are nice and anti-periplanar, what's great about a Newman projection with an E2 is that this is where you're making your double bond, and your Newman projection is literally frozen right there. So I draw my double bond right where the Newman projection is. So these are matching, okay? And then this side has a methyl and an ethyl. That is here and here. And now this side has a hydrogen and a methyl. So here and here. And then you'll always get your drawings right. Now I can spin that around. That's the same as also drawing it like this. So I can draw it. Let's spin it just a little bit. And then we'll spin it here. How about like that? So all I did was just rotate it. And now we've got our pink on the top and our orange on the bottom. Okay, now one last thing. This is what makes E2 some of my favorite problems. Is this cis or trans? Huh, it's neither. Do you notice we only have one hydrogen? So we need to use a different naming system, and that is called our E and Z system. So let me show you how to do that, and then we'll stop our video. So when you've got a double bond, we're going to rank it like our stereocenter. Let me redraw this one, and then I'm going to draw the other one so you can compare. There are two versions of this one, okay? And then we're going to just bring it all home and refresh. So when we look at our double bonds, I'm going to cut it like this, and I'm going to rank each side. And now this isn't as bad as a stereocenter because it's not a stereocenter. We don't have three things there. We only have two. So I'm going to just rank low and high, probably like a card game, right? Low and high. And we follow the same rules as R and S. So then the difference between these two is that we have high, high, and low. So it's almost like on this one then, if you cut it this way, you have low on the same side, high on the same side. That is our Z. And I think of it as Z same side. Then if you look at this one, you have low and high on the same side. It's almost like a trans. That is your E. So they are different. And this will show up in front of the name. So you would name these as a 1, 2, 3, 4, 5 as a pent 2-ene. And then let's see, we have a methyl on number 3. And then we would put, so which one did we make in our reaction? Did we make the E or the Z? We made the Z, right? Because we have this one. So in our reaction here, we made the Z product. So the Z would be italicized out front. So what did we make in this whole thing? Holy cow, that was a lot of information. We made only one product, and it was the Z product. And that's because we had stereocenters there, and our reaction has to go through antiperiplanar. So we literally made only this one. We did not make the other one. Okay, I love it. Let's stop this video here. Now, this is something we need to practice in class on Tuesday. We'll see you soon.